Hi guys, this is O-level chemistry and we are doing moles and stoichiometry. Question 1. Zinc chloride is a soluble salt. It is prepared by the reaction of an insoluble base with a dilute acid. The equation for this reaction is shown, and the equation says that zinc oxide reacts with HCl to produce zinc chloride and water. A sample of 3.50 grams of zinc oxide is added to 50 cm cube of 1.2 mole per dm cube hydrochloric acid. Show by calculation that zinc oxide is in excess. So what we need to do here is we need to calculate the number of moles of zinc oxide as well as the number of moles of HCl, and comparing the two we need to show that the moles of zinc oxide are more than the moles of HCl that are required to react with it. So the first thing we need is the MR of zinc oxide. So looking at the periodic table, the AR of zinc is 65 and the AR of oxygen is 16, giving us a value of 81 as the MR of zinc oxide. And the next thing we need to do is to calculate the number of moles of zinc oxide. So moles of zinc oxide will be calculated using the formula N is equal to M upon MR. The mass given in the question is 3.50 grams. The MR calculated is 81. When we divide 3.50 by 81, we end up with number of moles of zinc oxide as 0.0432 moles. So this is the number of moles of zinc oxide. Next, we need to calculate the number of moles of HCl. So the number of moles of HCl would be calculated using the volume and the concentration of HCl given. So the concentration is 1.2 mole per dm cube, which means 1.2 moles of HCl are present in 1000 cm cube of a solution, because 1 dm cube is equal to 1000 cm cube. So how many moles would be present in 50 cm cube which was used? So this will be calculated as 50 upon 1000 multiplied by 1.2, and this would give us a value of 0.06 moles. Now that we have calculated moles of zinc oxide and moles of HCl, now we need to see which one is in excess. So comparing zinc oxide to HCl, according to the given equation, 1 mole of zinc oxide reacts with 2 moles of HCl. So the amount of zinc oxide that we have is 0.0432 moles. So the amount of HCl that would react with this much zinc oxide would be twice that of 0.0432, which gives us a value of 0.0864 moles. So the amount of HCl needed to completely react with zinc oxide present is 0.0864, whereas this is required and this is present. So 0.0864 is greater than 0.06, which means HCl is the limiting reactant, and this makes ZNO that is present in excess. So this is how we conclude that the amount of zinc oxide present is in excess, because the amount of HCl present is lesser than the amount of HCl that is required to completely react with the number of moles of zinc oxide present. Question 2. Calculate the percentage by mass of phosphorus in calcium phosphate. So the formula of calcium phosphate would be calcium has a charge of 2 positive and phosphate has a charge of 3 negative. So the 3 would be the number of ions of calcium present and 2 would be the number of ions of phosphate present. So the formula of calcium phosphate would be Ca3PO4 twice. So this is the formula of calcium phosphate. And now to calculate the MR of calcium phosphate. So MR of Ca3PO4 twice would be equal to, so the AR of calcium is 40, so that would be 40 times 3. Then we have got the AR of phosphorus as 31, so 31 times 2. Then we've got the AR of oxygen as 16, and this would be 16 times 4 into 2 is 8, so 16 times 8. And when we total this together, we end up with the MR of calcium phosphate as 310. So now we have the MR of calcium phosphate. What we need to do is we need to calculate the percentage by mass of phosphorus present in calcium sulfate. So percentage by mass is equal to the amount of phosphorus present is 31 times 2, because there are two atoms of phosphorus in one molecule of calcium phosphate. So this would be divided by 310, and we would multiply this by 100 in order to calculate the percentage. So the percentage comes out to be 20%. So in order to fill the answer, the percentage by mass of phosphorus present in calcium phosphate is 20%. Question 3. Oxides of nitrogen, such as nitrogen monoxide, are atmospheric pollutants. The exhaust gas from a car engine contains 0.00200% by volume of nitrogen monoxide. Calculate the number of molecules of nitrogen monoxide in 960 dm cube of exhaust gas at room temperature and pressure. 1 mole of any gas contains 6.02 into 10 to the power 23 molecules. So the first thing we need to do is calculate the volume of nitrogen monoxide in 960 dm cube of exhaust gas. So in order to do that, we would divide 0.002 by 100 and multiply it by 960, which gives us a volume of 0.0192 dm cube of NO gas present in the exhaust gas. Next, we would calculate the number of moles of NO present in this volume of the gas. So that would be 0.0192 dm cube divided by 24 dm cube, which is the volume of 1 mole of any gas at RTP. And this would give us 0.0008 moles of NO gas to be present in the exhaust gas. And lastly, we would calculate the number of molecules present in these many moles by multiplying this value 0.0008 by 6.02 into 10 to the power of 23, which gives us a value of 4.816 into 10 to the power of 20 molecules of NO gas. So the answer is 4.816 into 10 to the power of 20. Question 4. Zinc nitrate is a soluble salt. It is prepared by the reaction of an insoluble carbonate with a dilute acid. The equation for the reaction is shown. The equation states that zinc carbonate reacts with 2 moles of nitric acid, producing zinc nitrate, water, and carbon dioxide gas. A sample of 4.50 grams of zinc carbonate is added to 50 cm cube of 1.3 mole per dm cube nitric acid. Show by calculation that zinc carbonate is in excess. So the first thing we need to calculate is the MR of zinc carbonate, and this would be calculated by adding the AR of all the atoms present. So we have one atom of zinc, which would be 65. We have one atom of carbon, which would be 12, and we've got three atoms of oxygen, which would be 16 times 3. And we add these values together, we end up with an MR value of 125 for zinc carbonate. The next thing to do is to calculate the number of moles of zinc carbonate, and this would be calculated by using the formula N is equal to M upon Mr, which would give us a value of 4.50 as the mass of zinc carbonate divided by 125 as its Mr. And this gives us the number of moles of zinc carbonate as 0.036 moles. Next, we need to calculate the number of moles of HNO3. And in order to calculate the number of moles of HNO3, we need to use the volume and the concentration of nitric acid given. So the concentration of nitric acid is 1.3 mole per dm cube, which means 1.3 moles are present in 1000 cm cube. And the volume of nitric acid used is 50 cm cube. So we would need to calculate how many moles would be present in 50 cm cube. So this would be calculated as 50 upon 1000 into 1.3, and when we calculate these values we end up with 0.065 moles of HNO3 present. Now the molar ratio of reaction between zinc carbonate and HNO3 according to the given equation is 1 is to 2. So if the number of moles of zinc carbonate is 0.036 moles. The number of moles of HNO3 required to completely react with zinc carbonate would be twice the amount present. So that would be 2 into 0.036, which would give us a value of 0.072 moles. So 0.072 moles of nitric acid are required, whereas 0.065 moles of nitric acid are present. So 0.072 is greater than 0.065, which means the amount required is greater than the amount present. This makes HNO3 as the limiting reactant, which confirms that zinc carbonate is present in excess. Question 5. Calculate the percentage by mass of nitrogen in magnesium nitrate. Give your answer to two single figures. So the formula of magnesium nitrate would be magnesium has a charge of 2 positive, whereas nitrate has a charge of -1. So in order to find out the formula of magnesium nitrate, we would have 1 ion of magnesium present and 2 ions of nitrate present. So the formula of magnesium nitrate would be MgNO3 twice. The next thing we need to do is to calculate the MR of magnesium nitrate. So this can be done by adding together the AR of all the atoms present in the molecule. So that would be mass of magnesium, which is 24, added to the mass of nitrogen, which is 14. And since there are two atoms of nitrogen, so 14 times 2. And this is added to the mass of oxygen, which is 16. And there are 3 to the 6 atoms of oxygen present. So when we add all these values together, we get an MR value of 148. The next thing we need to do is to calculate the percentage by mass of nitrogen in magnesium nitrate. So the formula of magnesium nitrate is MgNO3 twice, meaning we've got 2 moles of nitrogen present. So the mass of one nitrogen atom is 14. So 14 times 2 becomes the numerator. The denominator would be the MR present, which is 148. And in order to calculate the percentage, we multiply this ratio by 100, ending up with a percentage value of 18.92%. And since it is stated that we need to give our answer to two single figures, so this will be rounded up to 19%. So the percentage by mass of nitrogen in magnesium nitrate is 19%. Question 6. A sample of clean dry air contains 0.0400% carbon dioxide by volume. Calculate the number of molecules of carbon dioxide in 480 dm cube of clean dry air at room temperature and pressure. 1 mole of any gas contains 6.02 into 10 to the power of 23 molecules. So the first thing we need to do is to calculate the volume of carbon dioxide present in 480 dm cube of clean dry air. In order to do that, we need to divide 0.04 by 100 and multiply this value by the volume, which is 480, which gives us a value of 0.192 dm cube of CO2 gas present in clean dry air. The next step would be to calculate the number of moles of carbon dioxide present, which can be calculated by dividing 0.192 dm cube by 24 dm cube, which is the volume of 1 mole of any gas at room temperature and pressure. And this gives us the number of moles of CO2 as 0.008 moles. The next step would be to calculate the number of molecules, and in order to do that, we multiply 0.008 by 6.02 into 10 to the power of 23, which is equal to the number of gas molecules present in 1 mole of any gas. And this gives us a numerical value of 4.816 into 10 to the power of 21 molecules of carbon dioxide gas. So the final answer is 4.816 into 10 to the power of 21. Question 7. Dilute ethanoic acid reacts with aqueous calcium hydroxide. And the equation is given. 2 moles of ethanoic acid reacts with 1 mole of calcium hydroxide to produce salt and water. A student reacts 25 cm cube of 0.01 mole per dm cube aqueous calcium hydroxide with dilute ethanoic acid using thermophthalein as an indicator. A volume of 12.5 cm cube of dilute ethanoic acid reacts exactly with 0.01 mole per dm cube aqueous calcium hydroxide. Calculate the concentration in mole per dm cube of the dilute ethanoic acid. So what we need to do here is we need to understand that there are two reactants present, a base and an acid. And in this question, we have been given the volume and the concentration of the base and just the volume of the acid. So when we are been given with such a situation, what we need to do is we need to calculate the number of moles of the substance whose volume and concentration are both given, which is calcium hydroxide. So step one would be to calculate the number of moles of calcium hydroxide. And how do we do that? We use the concentration, which is 0.01 mole per dm cube. So 0.01 moles are present in 1000 cm cube of the solution, because 1 dm cube is equal to 1000 cm cube, and the volume used is 25 cm cube. So we calculate how many moles would be present in 25 cm cube of the base. So the calculation would be 25 divided by 1000 multiplied by 0.01, which gives us the number of moles as 2.5 into 10 to the power of minus 4. This way, we have calculated the number of moles of the substance whose volume and concentration were both given. Then we use the equation and the molar ratio to find out the number of moles of the other solution, which is in this case CH3COOH. So in order to calculate the number of moles of CH3COOH, we use the molar ratio. Calcium hydroxide is to CH3COOH. So 1 mole of calcium hydroxide reacts with 2 moles of ethanoic acid. So the number of moles of calcium hydroxide is 2.5 into 10 to the power of minus 4. In order to react with this, the number of moles of ethanoic acid required would be twice that of calcium hydroxide. So 2 into 2.5 into 10 to the power of minus 4, which gives us a value of 5 into 10 to the power of minus 4 moles of ethanoic acid. Now, since we know the number of moles of ethanoic acid, we need to find out the concentration of ethanoic acid. So concentration of CH3COOH can be calculated by putting together the number of moles of ethanoic acid calculated and the volume of ethanoic acid needed as given in the question. So This gives us 5 into 10 to the power of minus 4 moles of ethanoic acid are present in 12.5 cm cube, because 12.5 cm cube of ethanoic acid was added. And in order to calculate the concentration, the units of concentration are mole per dm cube. So per dm cube means in 1000 cm cube. So we calculate how many moles would be present in 1000 cm cube. So the calculation would be 1000 divided by 12.5 multiplied by 5 into 10 to the power of minus 4. And this gives us a value of 0.04 mole per dm cube as the concentration of ethanoic acid. So the answer would be 0.04 mole per dm cube of dilute ethanoic acid. Question 8. Dilute ethanoic acid reacts with sodium carbonate. And the equation is given. 2 moles of ethanoic acid reacts with 1 mole of sodium carbonate, producing 2 moles of salt, 1 mole of water, and 1 mole of carbon dioxide gas. Calculate the volume measured at RTP of carbon dioxide produced in cm cube when 3.18 grams of sodium carbonate react with an excess of dilute ethanoic acid. So the first thing we need to do is calculate the MR of sodium carbonate, Na2CO3. Since sodium carbonate contains 2 atoms of sodium, so that would be 23 times 2, added to 1 atom of carbon, which is having a mass of 12, added to 3 atoms of oxygen, which has a mass of 16 times 3. And this added together gives us a value of 106 as the MR of sodium carbonate. The next thing we need to do is calculate the number of moles of sodium carbonate, which is calculated using the formula N is equal to M upon MR. The mass given in the question is 3.18 and the MR calculated is 106. When we divide 318 by 106, we end up with a value of 0.03 moles of sodium carbonate. So now we have the number of moles of sodium carbonate present. We need to calculate the volume of carbon dioxide produced. So according to the given equation, the molar ratio of Na2CO3 is to carbon dioxide is 1 is to 1, which means if the moles of sodium carbonate is 0.03, then the moles of carbon dioxide is also 0.03 moles. And in order to calculate the volume, we multiply 0.03 into 24,000 because the volume needs to be calculated in cm cube, and 1 mole of any gas at RTP occupies a volume of 24,000 cm cube. So the number of moles of carbon dioxide present is 0.03. So we multiply 0.03 by 24,000 and we end up with a volume of 720 cm cube of carbon dioxide gas. Question 9. A compound of phosphorus, oxygen, and chlorine contains 20.2% phosphorus, 10.4% oxygen, and 69.4% of chlorine by mass. Deduce the empirical formula of this compound. So, in order to calculate the empirical formula, what we need to do is we need to calculate the ratio by dividing the percentage by the AR of each element. So, the elements present are phosphorus, oxygen, and chlorine. So what we need to do first is we need to write down the percentages of each of these elements present. So that is 20.2% of phosphorus, 10.4% of oxygen, and 69.4% of chlorine. And then we divide this by the AR of each element. So the AR of phosphorus is 31, AR of oxygen is 16, and the AR of chlorine is 35.5. Next, when we divide these values, we end up with a value of 0.65 for phosphorus, 0.65 for oxygen, and 1.95 for chlorine. The next step involves dividing these numbers by the smallest value amongst them, which is 0.65. So divide each of these values by 0.65. So for phosphorus, the result is 1, 0.65 upon 0.65. Same thing for oxygen. And when we divide 1.95 by 0.65, we end up with a value of 3 for chlorine. So the ratio of phosphorus to oxygen to chlorine is 1 is to 1 is to 3. Therefore, the empirical formula of this particular compound is POCl3. Question 10. Dilute hydrochloric acid reacts with aqueous sodium carbonate, and the reaction is 2 moles of HCl reacts with 1 mole of Na2CO3, producing 2 moles of salt, 1 mole of water, and 1 mole of carbon dioxide gas. A student titrates 20 cm cube of 0.0250 mole per dm cube aqueous sodium carbonate with dilute hydrochloric acid using methyl orange as an indicator. A volume of 15.5 cm cube of dilute hydrochloric acid reacts exactly with 0.0250 mole per dm cube aqueous sodium carbonate. Calculate the concentration in mole per dm cube of the dilute hydrochloric acid. So, we've got two substances, an acid and a base in this case. The base is the sodium carbonate, the acid is HCl. We have the volume and the concentration of sodium carbonate present, and only the volume of HCl that is used. So the first thing we need to do is calculate the number of moles of the substance that has the concentration and the volume given in the question, which is sodium carbonate. So step 1 would be calculating the number of moles of Na2CO3, and we would do that by using the concentration and the volume given. So the concentration of Na2CO3 is 0.025 moles present in 1000 cm cube of the solution, because the concentration is in mole per dm cube and 1 dm cube is equal to 1000 cm cube. And then we calculate how many moles would be present in 20 cm cube of the solution that has been used. So this calculation would be 20 divided by 1000 multiplied by 0.025, which gives us a value of 5 into 10 to the power of minus 4 moles of sodium carbonate. The next thing we need to do is we need to use the given equation to calculate the ratio of the reaction between sodium carbonate and HCl. So according to the equation, 1 mole of sodium carbonate reacts with 2 moles of HCl. So the number of moles of sodium carbonate present is 5 into 10 to the power of minus 4, which gives us the number of moles of HCl as 2 into 5 into 10 to the power of minus 4, which gives us a value of 1 into 10 to the power of minus 3 moles of HCl. So what we calculated here are the number of moles of HCl. Now, since we have the number of moles of HCl and the volume of HCl used is given in the question as 15.5 cm cube, we can use both these values to calculate the concentration of HCl. So step 3 would be calculating the concentration of HCl by using the given volume, which is 15.5 cm cube, and equating it with the number of moles of HCl that were present, which were obtained through calculation, which is 1 into 10 to the power of minus 3. And since we need to know the concentration, we will calculate the number of moles of HCl present in 1000 cm cube of HCl, which is equal to 1 dm cube. So the calculation would be 1000 divided by 15.5 multiplied by 1 into 10 to the power of minus 3, giving us a concentration of HCl value as 0.0645 mole per dm cube. Question 11. Calculate the volume measured at RTP of carbon dioxide produced in cm cube when 2.65 grams of sodium carbonate reacts with excess hydrochloric acid. So the first thing we need to do is calculate the MR of sodium carbonate. So MR of Na2CO3 can be calculated by adding together the masses of the atoms present in the molecule. So that would be 2 atoms of sodium. So that would be 2 times 23 added to 1 atom of carbon, which is 12, added to 3 atoms of oxygen, which is 16 times 3, which is equal to 48, and we add all these together to obtain an MR value of 106. The next step is to calculate the number of moles of sodium carbonate, and the number of moles of sodium carbonate can be calculated using the formula of M upon Mr, M being the mass, which is given as 2.65 grams. Mr has been calculated as 106, and the number of moles of sodium carbonate present is equal to 0.025 moles. The next thing to do is to calculate the molar ratio of sodium carbonate and carbon dioxide gas given in the equation, which is equal to 1 is to 1. Therefore, if the moles of sodium carbonate is 0.025, then the moles of carbon dioxide would be 2. Actually, it's not 1 is to 2, it is 1 is to 1, because if you can see that 1 mole of sodium carbonate reacts with 1 mole of carbon dioxide. So the number of moles would remain the same. So it would be 0.025 moles of sodium carbonate equal to 0.025 moles of carbon dioxide. Then we calculate the volume of carbon dioxide by multiplying 0.025 by 24,000, because we need the volume in cm cube, and 1 mole of any gas at RTP occupies a volume of 24,000 cm cube. So this gives us a volume of carbon dioxide as 600 centimeter cube. Question 12. A compound of sodium, iodine, and oxygen contains 11.62% sodium, 64.14% iodine, and 24.24% oxygen by mass. Reduce the empirical formula of this compound. So the first thing that we need to do is we need to divide each of these percentages by the AR values of these elements. So the AR of sodium is 23, the AR of iodine is 127, and the AR of oxygen is 16. And when we divide these values, we end up with a value of 0.505 for sodium, 0.505 for iodine, and 1.515 for oxygen. The next step is to divide these values by the smallest number amongst them, which is 0.505. So we divide each of these values by 0.505. And when we divide 0.505 by 0.505, we end up with a value of 1 for sodium, 1 for iodine, and dividing 1.515 by 0.505, we end up with a value of 3 for oxygen. So the ratio of sodium is to iodine is to oxygen is 1 is to 1 is to 3, making the empirical formula of this compound as NaIO3.